Amides. Let's take a look at the amides structure first, right? So then we'll delve into the more advanced features, of course. So basically for amides, what we need to do is identify the carbonyl group, right, in our compound. And this carbonyl group now will be attached not to nitrogen, not to chlorine or H or OH, right, or O alkyl, but to the nitrogen atom, right? And in turn, the nitrogen atom can be, so here we have some kind of like alkyl chain typically, right? Maybe like methyl, ethyl, whatever, right? So typically alkyl chain to begin with. So, and now here we have our options, right? So we can have like one amide, which will contain just NH2 here. Another subclass of amides will be like this, right? So again, guess what? We are going to make some substitutions, right? Instead of H, we are going to have maybe a methyl, right? So that's going to be another possible amide class. So finally, we can like completely substitute both of those H's and switch them to some other, like maybe like more exciting group potentially, right? So maybe here we'll have, let's say, isopropyl, and here we have also isopropyl. That's another type of amides which are like out there, right? So yeah, these are our amides. So as you see, they all have something in common, such as kind of this alkyl chain, CON, and like various things attached to the nitrogen in turn, right? So nitrogen is trivalent everywhere. So yeah, there are definitely similarities and differences, right? So this is something to pay attention to when you try to like wrap your like mind around this like myriad of structures, right? So then what else? So amides or amides are typically named after the respective carboxylic acid from which they were derived, right? So for example, if you take a look at, let's say, maybe like acetic acid, right? So uh, it's going to be looking like this, right? So that's acetic acid, COOH, right? So now if you basically like remove the OH, right? So and switch it to NH2, you are going to make not acetic acid, not acetic acid amide, but acetamide or ethanamide, right? So which is going to be looking like this, right? So we have CO, and here we have just NH2, right? So if we have the maybe propanoic acid, right? So we are going to make like this compound, which is going to be called propanamide, right? Propanamide. You see, you use the root from the like parent alkane, right, with the respective number of carbons, and then add amide, the word amide. So then if you have like a butanoic acid, guess what? You are going to produce the butanamide, right? So one word from this like respective butanoic acid, right? So then sometimes we deal with something more complicated, right? Such as maybe we have amide like this, right? So let's have maybe like 1, 2, 3, 4, 5, 6. 6 carbons, right? So 6 carbons are right here. So then we have our NH with, let's say isopropyl, right? Our favorite isopropyl. So what do we have here? Turns out to name it, so you need to acknowledge, first of all, that on the nitrogen atom of the amide, you are going to have a substitution, right? A substituent, which is different from just an H, right? So it's going to be, in this case, isopropyl and isopropyl and isopropyl and isopropyl. And now we are going to take a look at this like respective, what's it called? Carboxylic acid from which it was derived, right? 1, 2, 3, 4, 5, 6. So it's going to be hexanoic acid, right? So we'll just retain the root, hexanamide, and isopropyl hexanamide, right? So that's the another nomenclature example for amide naming. So yeah, now let's move on to the like physical properties, right? So of the amides and some bonding. Let's take a look at the bonding, right? So in amides, so bonding in amides is possible. So because they contain or they can contain the NH bond, right? So in their structure. Consequently, you can envision the hydrogen bond in existence between molecules of amides. So we can show some sort of like random, like coincidentally, R can stand for random amide, which is going to be looking like this, right? So we have NH2 here, and now we have another amide molecule, right? So like somewhere nearby floating around. So that's going to be our molecule, right? So then, as you can see, if you draw several of them, that can form the entire like network of hydrogen bonding. So, and then we have here it is, the hydrogen bonding event. Delta plus on the hydrogen, delta minus on the oxygen. So electrostatic attraction will ensue, right? So then you can also have the hydrogen bonding, yeah, between like H's and oxygens, basically. That's where it's at. Typically in amides, right? So you can form like show another amide here somewhere nearby, right? So maybe it's going to be your carbonyl group, right? So and then you have like OH type hydrogen bonding. So lots of H's everywhere. And then again, you have here delta minus and delta plus, and you can like draw that and then you kind of like instill this like skill of drawing hydrogen bonding between like various amide molecules. So yeah, that's pretty exciting. So because of this hydrogen bonding, turns out they can be solids, right? A lot of them are solids usually. So and then they will have high melting points as well. So then it was like experimentally determined that mono and disubstituted amides have lower melting points, right? But again, so yeah, now we have the trends, right? But again, those trends were obtained experimentally from the experimental, like empirical work, as we would say, right? So hydrogen bonding can also be present between the amides molecules and the water molecules, right? So if you show some sort of amide like this, maybe it's going to be like RCO NH, right? So I'm just looking at my notes as well. So then we're going to show the hydrogen bonding. So let's show the water molecule nearby, right? And then it will be like strategically positioning next to one another our partially positive, partially negative atoms, right, in the respective molecules. So delta minus is in the water, delta plus is in the water, delta minus is in the oxygen, right, of the amine. So now they form a bond, right? Oxygen, delta minus of the amine, H plus, H delta plus of the water, right? So now we have H with delta plus on the amide, right? Forming hydrogen bond with the oxygen with the delta minus from the water, right? Plus minus again. So the opposite charges will attract, as we know from physics. So yeah, they can form the hydrogen bonding with water molecules. And then again, it was experimentally determined that actually usually amides with less than 6 carbons, right, in their structure are typically water soluble, right? And then conceivably, yeah, as we go further, as we know, right, so like maybe to like 10 carbons, 20 carbons, and so on in the amide molecule, we are dramatically increasing the amount of the what's it called, non-polar character, right, in the molecule, and and then the solubility will decrease, right, because the water is water at all times, and then it cannot just change its structure, right? So water will be water, H2O. So and it is a polar molecule, right? So if you have a lot of like non-polar character in the molecule you're trying to dissolve in water, then you will have the non-miscible or immiscible mixture, right, between this kind of like non-polar molecule or the molecule with a significantly non-polar character and the water molecule. So yeah, something to keep in mind.